Hello and welcome to the first video of the FP2 chapter Maclaurin and Taylor series. This chapter involves a lot of differentiation, so a quick differentiation review on the screen, fill in the table, and if you've got time, write down the chain, product, and quotient rules for differentiation. Here we go. X to the n differentiates to nx to the n minus 1, sine goes to cosine, cosine differentiates to minus sine, e to the x does not change, natural log of x is 1 over x, and a to the x is a to the x times the natural log of a, and you can see that this follows this pattern because if a is equal to e, the natural log of e is equal to 1, and you just end up with e to the x. Other things that you should be familiar with but don't have to remember are these, but you should also be familiar with the chain rule, the product rule, and the quotient rule. In this chapter, we're going to extend differential notation to higher orders. That'll be quite quick at the beginning of this video. Then we're going to understand and use the Maclaurin series. The next video, we'll look at the Maclaurin series expansion for compound functions. Then the Taylor series expansion, so there's two forms of that. And then we will use these to solve differential equations. Yes, if you thought we had finished these, not quite. So let's start off with the easy one. Let's look at a bit of notation. We've done first order derivatives and second order derivatives. You are familiar with these, but we can have higher order derivatives. And we can use the same notation that we've been using. For example, the third derivative you could write like this. Or in the f notation, first derivative f prime, second derivative double prime. Many people do the third derivative with a triple prime, and then after that they go on to simple numbers or even Roman numerals. So you can write it like this. With the dy by dx, it's pretty obvious. You just keep changing this number here. Fifth derivative would look like this. One other thing to note for notation, and that is if you want to evaluate these, the nth derivative when x equals a, you know that with the f of x notation you just put the number in the brackets here instead of the x, but with the dy by dx notation you can put all of this in big brackets and then put the x value you're evaluating at down here in the corner as a subscript. It's not quite as common, but you might even see it written as x equals that number in the corner there. So this is doing the same sort of thing as putting a number in here. It's saying I want to evaluate this thing at this point. Quick example of that. If y is equal to the natural log of 1 minus x, evaluate the third derivative of y at the point x equals half. So first we need to find that. First derivative is equal to minus 1 over 1 minus x. Second derivative is equal to minus 1 over 1 minus x squared. And the third derivative, if I just change that into index notation, make it a little bit easier for myself, that is equal to 2, 1 minus x, and then the minus is still coming out the front. We have the minuses here even though the minus from the index is coming down because the minus inside the bracket is also coming out, so that minus is going to stay there. Then of course our index on the bracket is now a minus 3. So this is the expression that I need to evaluate when x equals a half. To do that, we just go ahead and put it in. Minus 2, 1 minus a half to the power of minus 3, and that's a half. Power minus 3 gives us 8. So the final answer there is minus 16. And to finish this fairly short section, we're just going to go through a bit more differentiation. Pause the video now if you want to fill this out before I start. We're just going to differentiate each of these functions on the left. First one, e to the 2x, gives us 2e to the 2x. Next derivative is 4e to the 2x, and then 8e to the 2x. Brackets, we need to bring the power down, 5, 1 plus x to the power 4, and then differentiate what's inside the bracket, but in this case that's only a 1. So this is the finished derivative. Next one, 21 plus x to the 3 and 61 plus x to the 2. X e to the x, we need to employ the product rule. That gives us e to the x if we differentiate x, and x e to the x if we differentiate the e to the x. To help see the pattern that's going to emerge here, I'm going to factorize that at the bottom here and write this. Then if we differentiate that again, e to the x does not change, and we have x e to the x, which again gives us another e to the x and x e to the x again. Factorizing that gives us e to the x 2 plus x. And you can probably see the pattern here. Differentiate this again, e to the x doesn't change, e to the x doesn't change, x e to the x gives us e to the x plus x e to the x. Factorizing that gives us e to the x 3 plus x. And of course I could have done that more easily by combining these, but I wanted to show how this progresses to give this answer here. Last one, natural log of 1 plus x. If we differentiate that, we get 1 over 1 plus x. And to help me differentiate again, I'm going to put that into index form. So when we differentiate that again, we get minus 1 plus x to the minus 2. But unlike the example before, this minus will disappear on the next one because there's no minus coming out of the bracket. So the next derivative, the third derivative, will be 2, 1 plus x to the minus 3. And at this point, if you wanted to, you could pause the video, go away and do exercise 7a. However, there wasn't too much new in that section, so I'm going to keep going into the next section where we can look at Maclaurin's series. So this is the key note here. For a continuous function, and it must be continuous, f of x, if the derivatives and the original function can all be evaluated at 0, another way of saying that is that they all have finite values, so there's no problem putting a 0 in any of these. We're not going to divide by a 0, for example. If that's true, then that function can be written as a polynomial series expansion like this, where the function is equal to the function itself evaluated at 0 plus its first derivative evaluated at 0 times x, second derivative evaluated at 0 divided by 2 factorial times x squared, and so on, and here's the general term here, and it keeps going. This is Maclaurin's series expansion for f of x. You won't need to derive where this comes from, although we'll talk about why it works in a moment. Here is a quick example to show you how powerful this is. Let's take our old friend e to the x, because when we differentiate that we know it doesn't change. So all of the derivatives are e to the x. I'll stop at the third one. Then we need to evaluate each of these at x equals 0. And again, because they're the same, that's really easy. Then we can put these into Maclaurin's series here. So f naught is equal to 1. So that goes there, 1. And this is a 1, 1x, so 1 plus x plus 1 over 2x squared plus 1 over 3 factorial x cubed. And if we stop at the third one, we get this. With some of these examples, you're going to have big numbers and you just leave the factorial in there. However, with a 2 and a 3, I think I would probably change that into a 2 and a 6. And because I've done up to the x cubed term and I've stopped there, although I could have done as many or as few as I liked, I have stopped on x cubed. This is called a Maclaurin polynomial of degree 3, because I stopped with the x power 3 term. So a little bit of a note on the naming of these here. And this is really great. It's useful because a lot of functions, although not all, we'll come back to that in a different video, a lot of functions can be expressed using this method. But why does it work? Before we go into the examples, I just want to show you why it works. So we've already said that this method won't always work. It won't work for every function, but we're only looking at the ones for which it will. So if f of x can be written as a polynomial, then we can write it in this very general form. And you know from work you've done on lots of different things, straight line equations if nothing else, that if you put x equals 0 in here, you find out the constant value here. Because if you put 0 in here, and all of these other terms have x, if they're all zeros, then all of these disappear. So f evaluated at x equals 0 must give you this value. So we can find this one quite easily. We just do f of 0, and that will tell us a0. But we can do the same sort of thing with all of the others. We just need to differentiate each time. If I differentiate this general form, then a0 differentiates to 0, a1x differentiates to a1, a2x squared differentiates to 2a2x, and if we keep going we get 3a3x squared, and if I put another one in there we get 4a4x cubed from a4x to the 4 here. I'll stop there, but you get the idea. Then we can put in x equals 0 again, and the same thing happens. All of these terms, plus all of the higher terms, they just become 0 because they all have an x in them. Whereas this one here, which is now a constant, is the only one that's left. So when we evaluate this at x equals 0, everything on this side, except for this, disappears. So that tells us the value of a1. If I write it like this, f1 of 0 tells us a1. And you might think, great, this should be really easy, but it does get a little bit more complicated because of the numbers coming out in front. So if I differentiate this again, the constant term differentiates to 0 again, then we get 2a2 plus 3 times 2 a3x plus 4 times 3 a4x squared, and then all of the other ones after that as well. And the reason why I'm not combining these is because this is where we're going to get our factorial from. So I'll leave those as they are so that we can see that. And again, if we put x equals 0 in here, all of these terms and the higher ones disappear, and this time we get 2a2, which is why we have to divide this one by 2. So that gives us second derivative evaluated at 0 divided by 2 equals a2, and 2 is the same as 2 factorial, so to keep to the pattern we put that in there. I'll do one more. The third derivative, the constant disappears again. Here we get 3 times 2, and to make it really clear where the factorial comes from, I'll put the 1 in there, even though you would not normally do that, plus 4 times 3 times 2a4x, and of course we've still got all of these going on, and each of these after this is following the same pattern. So the next one here will already have a 5 times 4 times 3, and when we differentiate again that'll have a times 2 in it as well. And here you can see that if we evaluate at 0, we get this thing is equal to this constant here. So the third derivative evaluated at 0 is equal to 3 factorial a3. So we just divide that through by 3 factorial, and that gives us a3, which is the coefficient of the x cubed term in the original polynomial. So I hope that's enough for you to see how this works. There is a caveat, however, and that is that sometimes the expansion is valid for a certain set of x. It's not always going to be valid for all x's. And that's a situation where if you put in a value of x, the series you get might diverge. In that case, it's not going to be very helpful. It's going to diverge to infinity. So there might be a certain limit on the x values that you can have, such that the series converges to an actual number. I think that's probably enough on the algebra. Let's have a quick look at the graphs. Here we've got e to the x plotted here, and its series expansion. Now if I plot the first two terms, just 1 plus x, that's a pretty poor approximation. But if I add in the next term, it gets a little bit better. The next term, quite a bit better. And as we keep adding terms in this expansion, you can see that the more terms we have, the better the approximation. By the time we get up to 7 terms, it's pretty good, and 8 terms is very good. Obviously, as this keeps going on, you might want a few more terms depending on how far down the graph you go, but up to this point here, that's pretty good. And if you go just up to x is equal to 2, you've got some very good approximations, even just with the first 5 terms. If you're not going to go above x equals 1, you've got some excellent approximations for pretty much everything beyond the first 2 terms. And even the first 2 terms aren't that bad. So that gives you an idea of how close the approximations are, and the fact that they are better with a lower x unless you're going to add more terms. Okay, I think that's enough on the concept. Let's get into a couple of examples. The final note here in the corner then, in general, the longer the series expansion, the closer it approximates the original function. First example, express the natural log of 1 plus x as an infinite series in ascending powers of x. Then, using only the first 3 terms of the series, find estimates for these. So we'll do 2 things here. We're going to use this to find an expression for this. So that's using the series expansion. We're also going to have an example here of using that to find an estimate for actual numbers. So first things first, we need the series expansion. We've got the function natural log of 1 plus x, and at 0 that is equal to 0. Now because that's a 0, I'm not going to consider that the first term. For the first term, what I want is something that's actually going to be a term in my final answer. So a 0 there, don't consider that your first term. We need to keep going. Differentiate this, and we get 1 over 1 plus x. Evaluating that at 0 gives us a 1. So that will be a term in my series, so that will be my first term. Differentiating again, we're going to get minus 1 over 1 plus x all squared, and evaluating that at 0 gives us a minus 1. So that will be one of the terms as well. So we've got 2 terms so far. We need to keep going. The third derivative, that will give us a 2 over 1 plus x all cubed. Evaluating that at 0 will give us a 2. So when we put all of this into here, we will have our 3 terms. F0, 0. First derivative is a 1 times x. So if I write natural log of 1 plus x is equal to, the first one was a 0, and then we've got x. And then the second one here, second derivative is minus 1 over 2 factorial, which is 2 times x squared. So we've got minus 1 over 2 x squared. And then we've got a 2 here, 2 over 3 factorial, which is a 6, 2 over 6 x cubed. I'll write it like this first, so the examiner knows what I've done, and then simplify it here, x minus 1 over 2x squared plus 1 over 3 x cubed. And these are the first 3 non-zero terms of this series expansion. Some people like to put on a plus dot 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 to show it's a series and we've only done the first few terms. Some people don't like to do that. I think it's fine either way. Now we need to use this to estimate these 3 things here. And this part is quite easy. We've got 1 plus x here, and we need a 1.05, so obviously x here is going to be a 0.5 here. So if I make that clear, 1.05 is equal to 1 plus 0.05, so my x value is equal to 0.05. The approximation then is found simply by substituting this value into this expression here. 0.05 minus 0.05 squared over 2 plus 0.05 cubed over 3. And that will equal 0.0487916 dot 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 dot. And then if I use my calculator to actually do the natural log of 1.05, we can compare that. It says 0.0487916. So it's correct up to here. 1, 2, 3, 4, 5 decimal places correct. That's pretty good. Let's have a look at the next one. B. Here we've got 1.25. Obviously that's 1 plus 0.25. So my x value is going to be a 0.25. And we do the same thing. Natural log of 1.25 is approximately equal to this with x is equal to 0.25. Stick that on my calculator, see what we get. 0.223958 ... And the real value, if I use my calculator to find that, is 0.22314. So this one is correct up to 2 to 3 decimal places. That's still not bad, that's still pretty good. But the way we're going, I suspect C will not be as good. Let's do C up here so we can still see all the other stuff. 1.8, 1 plus 0.8, so my x value is going to be 0.8. So natural log of 1.8 is approximately 0.8 minus 0.8 squared over 2, and I've just realized I wrote a plus down here. That should have been a minus, but I did use minus on my calculator. Sorry about that. Plus 0.8 cubed over 3, and that gives us 0.65066 ... And the real answer is 0.5877, so that's not even correct to 1 decimal place. I guess you could argue it's correct to the nearest whole number, but only just. So that's a pretty poor approximation, really. And you can see that what we had on the graph is seen to be true here, in the sense that the smaller the value of x, the better the approximation was. In order to get a good approximation out of this one, I would have to add more terms in this expression here. I don't know how many, maybe I'd have to go up to x power 5 or something like that. But certainly I would need more terms for this to become as accurate as even this one here, let alone this one here. That was a nice first example. Our second and final example of the video: find the first 4 terms in the Maclaurin series of sine x. Using the first 2 terms of the series, find an approximation for sine of 10 degrees. Okay, so we've got a function given to us is sine of x, and you can see already just from these 2 examples that the process involved here is very similar each time. You're going to find a bunch of derivatives, you're going to put x equals 0 into those derivatives, and then you're going to put all of your information that you get into the series expansion. The problem with this one here is that quite a few of these are going to come out as 0, because this first one here, sine x, is a 0, so I can't count that as one of my 4 terms. If I need 4 terms, I'm going to have to go beyond these 4 here. This one's okay, this will give us a 1, that will be one of our terms. This one, again, will be a 0. This one will be a minus 1. And actually we can see a pattern here. You wouldn't need to do the derivatives if you could see this pattern, that this is just going to repeat again. But just to make it really clear for you, I'm going to keep going with it. This takes us back to sine x. And that will be a 0, so we need at least 2 more. It's cosine. So that will be a 1, that's fine. Now I've got 3 terms that are non-zero, but I need 4, so I need to keep going. That's another 0, I still need to keep going. But this one will be a minus 1, which will be my 4th non-zero term. So there I've got 1, 2, 3, 4 non-zero terms. So when I put all of this information into here, I will get 4 terms out of this now. First one is one of the zeros. The second one is 1 times x. So sine of x is equal to x, and then 0 here for the x squared term, minus 1 over 3 factorial for the x cubed term. So that's minus x cubed over 3 factorial. And then for the fourth one, we've got a 0. For the fifth one, it's a 1, so that's a plus x power 5 over 5 factorial. For the sixth one, it's a 0, and for x to the power 7, it's minus 1. So we've got minus 1 times x to the power 7 over 7 factorial. And this is one of those situations where I would not work out the factorials because these numbers are just going to get too big. Again, if you wanted to, you could put a plus dot 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 on there, but you don't have to, I think, because the question specifically asks for the first 4. So not putting that on, I think, is justified. That being said, if you don't put that on, maybe do an approximate equal sign here instead of a strict equal sign. Okay, that was the series expansion. Now the second part of the question, using the first 2 terms, so just these 2, find an approximation for sine of 10 degrees. So we're just using these 2. And I put the approximate equal sign there because I won't put plus dot 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 on the end. But here is a really key point. If I put a 10 in here and a 10 here, which will give me 1,000 when I cube it, that's going to be a huge number, probably a huge negative number because of this. And I know that sine of 10 must be less than 1 because of how the sine function works. So something funny is going on here if I put a 10 in here, and I'm saying all of that to emphasize really strongly this must be in radians. Even if the question gives it to you in degrees, you must change this into radians when you put it into a series expansion. So 10 degrees is the same as pi by 18 radians. So that's what I need to use here. Putting that in then, you get pi by 18 all cubed divided by 3 factorial, which is 6. So the sine of 10 degrees, I've left the 10 degrees on the left because that's what they want in the question, even though I'm using radians on the right. That might be a little bit confusing, but it's not quite so confusing now that I've evaluated that, because I'm just going to write 0.1736446 dot dot dot. And if I do sine of 10 degrees on my calculator in degrees mode, I can tell you that the real answer is 0.173648. So it's accurate all the way up to this 4 here. That's 5 decimal places again. That's a really good accuracy for something that's just using 2 terms of the series expansion. And that should be enough for you to have a go at exercise 7b. And by the time you finish that, no doubt you'll be a little bit bored of doing the same process each time. But of course it gets a bit more interesting as your functions get more interesting. Don't forget your product and quotient rules. And maybe I'll see you in the next video for some compound functions.